Hey everyone, in this video, I'm going to look at how to do a regression in Stata and how to do some tests for the veracity of that regression model. So what I have here is I've opened up Stata and I have a do file open up in front of me. So we can start going through the commands. So the first thing I'll need to do is I'll need to bring in some data. I'm going to use some prepackaged data from Stata because then you can follow on if you choose. So what I'll do is I'll go sysuse and then I need to bring in the data. So sysuse and then auto, that will bring out a data set that has some basic information about cars. So that's going to give us some base data in order to do a regression. Now I've run the sysuse auto command here, and then I'm just going to go with browse so that you can look at what this data actually looks like if I actually get the spelling correct. So one common tip here is if your do file is failing, it could just be due to spelling errors. All right, so now we're browsing the data. Now what you'll notice in the data is it's a cross-sectional data set. We have an observation for each make and model. We also have the price of each car, miles per gallon. We have things like the weight of the car, the length of the car, etc., etc. Now, I'm not going to go into the details here. The purpose of this is just to determine what types of things might go into a regression model as opposed to getting an idea for what things really determine car prices, for example. I just want to use this as an example. So what you'll notice here is we have a whole lot of variables here that are numerical. We also have one indicator variable for whether it's foreign or domestic. The reason that's important is an overseas-based car can have import duties imposed upon it, which might, for example, make it more expensive. So if, for example, we were to run a regression model looking at what factors determine price, whether it's foreign or domestic is going to be particularly important because of those tariffs that might be imposed. It would be even more important to know about the exact location it's from because tariffs can sometimes vary. However, this gives us a bit of a blunt object here. What you'll also notice is that many of these variables, for example, price here and weight, are very large and potentially very, very skewed. And this is going to mean that when we put these into a regression, we might want to take the natural log of these in order to mitigate some of that skewness. In order to look at some of the skewness here, we can run histogram. And histogram say price. And what this is going to tell you is we might end up with quite a bit of lumpiness here. So for example, I've run the histogram here. And what you'll notice here, unsurprisingly, is there are no negative prices. However, you'll notice there is this quite long tail and quite a bit of potentially kurtosis if this were a normal distribution here at the very low prices. So it might be useful for us to take the natural log of this. So let's start doing a regression here. So I'll bring back my do file. Now what I might want to do first is, like I said, I'll generate some natural logs. So go gen ln price is equal to ln and then price plus 1. Again, you add plus 1 to it. Obviously, there are no zero prices here, but just in case there is a zero, it is good practice to add 1. In general terms, given the sheer magnitude of the prices here, adding 1, like literally 1 to the price, is not going to create a qualitative difference in your regression outputs. However, it would prevent any situation where there happens to be a 0 creating a missing value. So it's generally good practice to add 1. So we'll go gen ln price, and then I'll go log weight as well, is equal to ln of weight plus 1 rather. All right, so now I need to execute those selections. Now it's good practice again to execute line by line just in case there are typos. So I have price and I have weight. Now, what you'll notice here is these are both non-zero because all of the prices and weights were quite large. So we're not going to end up with any negative values here. That means that you might want to consider something like a turbot model when running a regression, but that's really beyond the scope of this video. I'm just going to look at a plain regression here. So what we next might want to do is just run a basic regression. Now I'm going to run a basic regression without any options added to it. So I'll go with regress, which is the regression command. Then I need to put in my dependent variable and then my regressors or my independent variables. So that's the general syntax. So regress, then dependent variable. So for example, say I want to look at the factors that determine price. I go ln price as my dependent variable. Then I need to put in the regressors, so the things that might influence price. So I'll go, for example, with ln weight, and then we saw mpg, so miles per gallon before, and then I might also add, as an example, foreign or domestic, so the indicator for whether it's foreign or domestic. So that's just an example. So I've chosen some variables here, almost at random, just to give you an illustration. Now, this regression model has no options added to it. Those options, to some extent, are things that we do after initial regression diagnostics. So, for example, I haven't brought in robust standard errors at the moment, haven't clustered standard errors either. So that's some things that I have not put in. I also have not put any other additional fixed effects. So that's something that can be done in other types of data sets, which I'm going to leave to the side for the moment. So let's run our regression and see what the output is like. So we're on the regression, and then Stata gives me this regression output. So there's a few things to note here. Firstly, it gives me the number of observations. So here I have 74 observations. I do not have many observations in this regression. Next thing to note here is I have the R squared and the adjusted R squared. The R squared is basically telling you how much of the variation in your dependent variable is explained by variation in your regressors. So here it's about 49% under the ordinary R squared, 47% under adjusted. The adjusted R squared essentially penalizes the model for having too many regressors. So here, quite a large amount of the price is explained by our regressors in this particular data set. What constitutes a good R squared depends on what is standard in the field that you are researching. And there are different acceptable levels of R squared for different things that you are looking at. We also have various other regression diagnostics up here, which I'm not really going to focus on because oftentimes these are kind of caught up in the other diagnostic commands we can do. Now, down in the bottom table here, what you'll notice is we have this table of regression coefficients. So our dependent variable is the log of the price. Then we have various coefficients here. The first 3 lines in that table tell us the coefficients on our regressors. The final line in the table tells us the coefficient on the constant, so the alpha term in our regression here. So what we have here is, firstly, we have ln weight. The coefficient on the log of the weight is 1.21. So that tells us heavier vehicles cost more. That could be because those heavier vehicles are often trucks and the like, which have particular commercial uses. So that could be why. So these heavier vehicles cost more, and the p-value is very close to 0, which tells us that this is statistically significant, which tells us the coefficient here is statistically different from 0, which is what this p-value is testing. MPG is the coefficient is negative, but it is not statistically significant. Now, admittedly, this could be a function of the data being slightly dated. So there are various points in time where miles per gallon is relevant. During the time in which this data was collected, maybe it was not relevant. In any case, it is not statistically significant in this particular data set. The foreign indicator is significant, and it's quite positive at 0.5. So foreign vehicles are costing quite a bit more. So the p-value here is 0. Again, this is statistically significant. This could, for example, reflect import tariffs, which cause overseas-based vehicles or overseas developed vehicles to cost more due to the costs of importation. So those are some things that we have from our regression model. What we can next do is we can start on some regression diagnostics. So to start on some regression diagnostics, what we will want to do here is we'll need to get some various outputs from our regression model. To get these outputs, we need to use the predict command. Predict tells Stata, give us some variables that can be generated from this model. So for example, we can generate predicted values, or we can get residuals, or we can get some various other things from this. So for example, say you wanted the predicted values from the model. I would go here, predict, as my command, and then I type in the variable name, so ln price underscore pred, just ln price predicted, you can call it whatever you want, then comma, and then xb. xb is basically telling me, or telling Stata rather, give me the predicted variable or predicted value. So if you just run this, it will run this and give me predicted values. We will be able to compare the predicted values versus the actual in a second, but we'll do that after I've generated some other predicted values. I'll also want to generate the residuals. So go predict, and then, for example, say I want the residuals. I'm just going to call that resid, and then I do comma, then resid, and that will give me the residuals. And then the final thing that I want to do for predicted values here is I want to create what's called the Cook's D. Cook's D is basically a measure of how much influence those points have over the regression output. It creates a variable, and that gives you an observation number for each of the individual observations. It's basically telling me which of my observation points exert a lot of influence over the regression output. It's a way of detecting outliers. And a particularly high Cook's D might tell you that maybe there's an outlying point. So what I'll do here is I'll go predict Cook's D, and then I'll also call that Cook's D. All right, so that's what we have for the predicted values. And now I'll just generate those to make sure there are no typos. So that has worked perfectly okay here. So what I next want to do is I want to perhaps check for leverage points. Now, checking for a leverage point is useful because it tells you, are there potential outliers? When there are outliers, you don't necessarily want to drop them, but you do want to see what is going on when you're running your regressions. So what we do here is we'll use Cook's D. Now, a general rule of thumb is that a point might be an outlier if it is more than 3 times the mean of the Cook's D. So in order to test this, what I'll do is I'll go summarize Cook's D, and this will just give me various summary statistics for Cook's D. So there's nothing particularly special about this. It gives me the mean, the variance, the standard deviation, etc., etc. So we'll go summarize Cook's D. Now, after I've done this, I can then generate a leverage point indicator. So I might go gen leverage point, and then I'll call that as an indicator. So I'll go gen leverage point equals 1. So it equals 1 if Cook's D is more than 3 times the mean. So that would be greater than 3 times then R mean. Now, the reason I go R mean is the R function here is basically telling Stata, recall the mean that you just generated from the summarize command. So I'll generate that leverage point indicator, and then we can see that there are 69 missing values, and we can count up how many leverage points there are. So what I'll do is I'll go tab leverage point, so tab leverage point, and this will tell me that there are 5 leverage points here, or 5 potential leverage points. So when we've got 5 potential leverage points here, this tells us that some of those might be outliers. I would not necessarily automatically exclude those, but they're things that you might want to investigate. So for example, we can browse if leverage point is equal to 1. And this enables us to, for example, check out what things are going on here. So you'll notice here that there are some potential leverage points here where they potentially have, in this case, very high prices. So we're exerting a lot of influence, or quite low prices. And these are potentially situations where there's a weirdness in terms of price and weight metrics. Now, I'm not going to go into these in detail. However, you'll need to look at these in detail when you're running your particular regression to determine if they are genuine outliers or whether they are just ones with potential different results in them. If it's an outlier due to, say, a data error, then you would cut it out. However, if it's just an unusual point, you would generally not exclude it just because it's unusual. Rather, you would exclude something if there was a genuine data error. So, for example, if someone entered in price, there was like 100,000 here, when in reality, it's pretty obvious it should be 10,000 because there was a data entry error, then you might want to either correct that error or exclude it if you can't correct it. So that's basically what you're looking for here. Outliers that are due to problems with how the data was collected, essentially. And if it is the case that there are lots of leverage points, it might tell you you need to do a better job going out and collecting the data. In any case, that's an initial test. Now, the next thing that I might want to do is I might want to test for this heteroscedasticity. So in order to do this test, what I need to do is I need to go estat het test. Now, this is going to tell Stata to do a heteroscedasticity test. So let's run that. And what you'll notice here is our initial hypothesis here, so our null hypothesis, is that there's constant variance. Our alternative hypothesis is that there is not. So here, we cannot reject the null hypothesis. We know we cannot reject the null hypothesis because here, basically, the p-value is super high. As a result, we can't reject our null of constant variance. That's good for us. So it tells us there's probably homoscedasticity here, which is what we want. So as a result, our heteroscedasticity test is turning out in our favor for the regression model working okay, basically. So we don't really need to do terribly much to adjust for that. In general terms, it is generally good practice to put in robust standard errors into your regression model in any case. However, it doesn't appear to be necessary here. So that appears to be functioning okay for us. We cannot reject the null of constant variance or heteroscedasticity, which tells us at least that portion of the regression model is behaving acceptably well. The next thing that we might want to do is we might want to test for multicollinearity. Now, multicollinearity is something that you need to bear in mind, but it is not fatal to a regression model. Multicollinearity is important in that multicollinearity tells you how much are the regressors that you have highly correlated against one another. If they're highly correlated, that tells you, well, potentially then you need to deal with that correlation and perhaps consider whether some of those variables need to be dropped because they're capturing the same thing. However, it's better to have multicollinearity than to have omitted variable bias. So what we'll do here is we'll go EStat, and then after EStat VAF. This is going to give us our variance inflation factor, so I'll go with that. And then what you'll notice here is our VAFs are not especially large here. There is going to be quite a decent amount of correlation between weight and, for example, miles per gallon. But what we're basically looking for here is there a VAF of greater than 10? And here it appears there isn't one. Now, 10 is just a general rule of thumb. However, it appears there isn't multicollinearity. However, there appears to be a decent amount of correlation between these regressors. If we also want to check out the correlation between regressors, we can use PW_core. So to do that, we go PW and then CORR, so PW_core, and then I'll just copy paste in my regressor variables here. And I've also got my dependent variable as well, just for good measure. I run that command, and what you can notice here is there's a decent amount of correlation, for example, between weight and miles per gallon. That's telling us there's a pretty decent risk of correlation and multicollinearity. So it's something you do want to bear in mind. If you really want to adjust for this, you probably would want to use something like principal components analysis, because principal components analysis is going to help to get around some of this. Furthermore, there's quite a high correlation between foreign cars and weight as well. So let's have a look at the p-values associated with that. So we can go sig as an additional command in the PW_core thing, and this is then going to get us our p-values. And what you'll notice is these high correlations are statistically significant. So if you're really concerned about this, the solution is going to be something like principal components analysis, which is beyond the scope of this video. The solution is not going to be dropping these variables, because dropping the variables is probably going to create omitted variable bias, which is worse than multicollinearity. Multicollinearity biases your standard errors toward being 0 on average. However, omitted variable bias will bias your coefficients toward being completely wrong and potentially erroneously statistically significant. This is important to bear in mind, and it's something you might want to resolve if you were to go further and use a data set like this. All right, so those are our initial couple of diagnostic tests. We can also run some basic plots as well. So for example, we can run a scatter plot of the residuals versus the predicted. So to do this, I'd go scatter, and then I'd go resid, which is going to be my residuals, and then I need to bring in the predicted value. So the predicted variable I created was ln price pred. So ln price underscore pred. And this is then going to give me a scatter plot of the residuals versus predicted. So I've run that scatter plot. And what this tells me is the scatter plot is kind of random looking. You can't really see some clear pattern. It's just this random cloud of dots, which is basically what I want here, because a random cloud of dots is kind of what you'd want from a regression model, because it tells you there's a degree of randomness with your residuals, which is what you're looking for. So that diagnostic test also clears okay. We can also go scatter of the actual versus predicted. So scatter of ln price versus ln price underscore pred. Now here what we're looking for is hopefully a actual relationship between the two. So I run this, and what you'll notice is there is kind of a linear model, but it's not perfectly linear. It appears to be slightly non-linear, which means that we probably need to make some adjustments here to the regression model. So for example, you might want to take various iterations of either A, more regressors, which might potentially resolve this, and or B, we might need to look at as well whether log transform is creating issues. So it could be worthwhile testing a regression where there is no log transform to see what that looks like. The next thing that we might do here is we can go histogram residual. Now we might want to check for normality in the residuals. So we'll go histogram and then we'll go resid. And this will tell us whether there's normality in the residuals, or at least give us a bit of an idea. So here the residuals don't look perfectly normally distributed. It's not terrible, but it's not great. So the reason it's not terrible is it looks kind of like what you would expect from a normal distribution, but not really perfectly. I.e., this point here, just after the 0 and the bit at around the point 2, it would be better if those were swapped around. That would look more normal. However, it's not disastrous in that it's not perfectly normal, but it's not telling us that there's super weirdness going on, is basically what I'd say. So it's not going to be fatal to the model, is probably the best way of putting it. However, there are probably some issues with the residuals, and you probably would want to use robust standard errors in this regression in order to deal with some of the issues that might arise. We can also further check this with the Q-norm and P-norm plots. So we'll go Q-norm, and then I'll go resid. And then I can also run P-norm, and I'll show you the difference in just a second. So Q-norm is going to give us a residual plot. What you're looking for is things that are basically hovering around this 45-degree line. Usually you'll get like an S-type shape. This is telling us they're probably close to normal, but not totally normal. The reason I say that is there's quite a bit of deviation systematically toward the 0 end, and seemingly a bit of deviation toward the high end. So it's not perfectly normal, but it's not totally terrible, is probably the best way of putting it. We can also go P-norm, resid as well. So P-norm resid, run that command, and you'll end up with a similar graph. Again, this is a bit closer to the line, but you can see that there's some deviation from it. Ideally, you'd want it to be closer and closer to the line. However, you're generally not going to get it perfectly on the line. Just from an empirical standpoint, that basically never really happens. So this is not a terrible plot. A terrible plot would be one where there's significant deviation from this 45-degree line that you see here. So that's what our regression diagnostics look like. We can also make some amendments to the regression. So say, for example, I have the regression model here. I mentioned we might want to also check what it looks like when we have, for example, no log transforms. So let's copy paste our regression model here, run the regression, and then I'll go regress. Then I'll just go price versus weight, and let's see what that looks like. So we do that regression. Again, we end up with some very, very weird coefficients. And you can see here why I did the log transform. The reason we end up with some really weird coefficients is due to the sheer amount of skewness in the price here, and the fact that there's a very large number, again, leading toward that skewness. And we want to try to tamp down on that skewness. So you notice here some massive coefficients, like on the foreign indicator, on miles per gallon, and also weight. This is going to be a much more difficult to interpret model. The coefficients are of similar statistical significance as before, but there are still potentially some issues. So we can again get our predicted values and our residuals and see what our scatter plot looks like to see if it performs any better. Because we might want to check, well, actual versus predicted doesn't do any better when we don't do the log transforms. So let's go predict, and then go predict, say resid2, resid. I'm just calling resid2 just for the sake of argument here. And then I go predict xb2 and then xb. So this is basically just going to tell Stata to give me my next set of residuals and predicted values. So go predict here, and then what I'll end up with is I can do my scatter plot. So go scatter, and then what I want to do here is I want to go scatter of the actual versus predicted. So scatter of xb2, and then I want to go with the actual, which is price. So let's go with that scatter plot and see how this performs. This graph is not better than what we had before. What we had before was a more systematic relationship than what we have now. This could be because when we don't do the log transform, we ended up with a much more difficult to interpret model due to the influence of outliers not being tamped down. So the log transform was doing a better job here. Now, if we go back to our initial model, what initial changes might I make to the model? So I'll just copy paste this model, and then I might start making some changes. So in terms of changes, what I'd want to do first is I want to add robust. Robust is going to make sure the standard errors are effectively heteroscedasticity resistant. So we'll go regress, robust. Results are pretty much the same. Robust makes some changes to the standard errors, but otherwise everything looks pretty much the same. Now the p-values are marginally different for a couple of them. So it's marginally different for MPG and marginally different for the constant. But it has not made much difference at all, which is not terribly surprising. It generally doesn't make a huge difference. However, it's still worth always putting that in because it's just worth doing it. It never makes the regression model worse. It can make an incremental improvement. What we also might want to do is cluster our standard errors. This might tell us that maybe hypothetically, some of the standard errors for different groups are going to be slightly different from one another. So for example, there might be different standard errors for the group of foreign cars versus domestic, hypothetically. So for example, if overseas cars had a particular reputation for having diesel-related scandals, then in that case, their price might be systematically slightly affected. In any case, you can cluster things by groups that you think are particularly important. So what I can next do is I can run my regression and I'll put in a cluster command. So I'll copy paste this regression here. And I pasted rather, so I'll copy paste the regression again. And then after I've done this, I need to use the cluster command. So what I'll do here is I'll go robust and then cluster and then foreign. And this is going to cluster the standard errors by foreign. The robust command is then going to ultimately be redundant. However, I've now clustered it by whether there were foreign or domestic cars. Now what you'll notice is this makes a significant difference to the standard errors. It makes a significant difference to the p-values here. A number of the p-values are much lower. This tells us that clustering makes a significant difference to our regression model. That tells us that potentially there are some different standard errors between the foreign and domestic groups. So here, it was important to cluster those standard errors. So here, for example, the p-value on weight has gone up marginally. It's still very statistically significant, but it's gone up marginally. The p-value on foreign has gone up quite a bit. It is now only statistically significant at 10%, whereas it was at 1% before. So it has made a difference here. So those are a couple of changes that you could potentially make to your model based on the statistics that we ultimately got. In any case, that's how you might go through doing a regression in Stata, some of the post-estimation commands you can get from Stata, and how you run some tests for things like heteroscedasticity, normality, and the like. In any case, I hope this video has been very useful for you, and I hope very much to see you for future videos as well. Bye.